Welcome to today's problem walkthrough. We'll be solving problem number 1496, path crossing. This is an intriguing problem that involves determining whether a path on a Cartesian grid crosses itself. Stick around as we explore the solution step by step. In this problem, you are given a string called path, where each character represents a movement direction on a 2D grid. The directions can be north, south, east, or west, represented by the characters n, s, e, and w, respectively. The movements start at the origin, which is the coordinate 0, 0, on the grid. Your task is to determine if the path ever crosses itself, meaning if it revisits any position that it has already visited after the starting point. The output should be a Boolean value, true if the path crosses itself and false otherwise. The input string path will have a length between 1 and 10,000, and it will only contain valid movement characters. Now let's look at some examples to better understand the problem. In the first example, the input is path equals NES. The path starts at the origin, 0, 0. The first move, n, takes it to 0, 1, followed by e, which moves it to 1, 1, and then s, which brings it to 1, 0. At no point does the path revisit a position it has already been to, so the output is false. This indicates that the path does not cross itself. In the second example, the input is path equals NESWW. Starting at 0, 0, the first move n takes the path to 0, 1, then e moves it to 1, 1, and s brings it down to 1, 0. The next move w takes it back to 0, 0, which is a position it has already visited. This means the path crosses itself, and the output is true. The crossing occurs when the path revisits the starting position. In the third example, the input is path equals ENWN. The movements proceed as follows: e moves to 1, 0, another e moves to 2, 0, n moves to 2, 1, w moves to 1, 1, and the last n moves to 1, 2. Throughout this path, each position visited is unique, and no position is revisited. Thus, the output is false, as the path does not cross itself. This example demonstrates a more complex path without any crossings. Finally, let's consider some important edge cases and constraints. A path with only one step, such as path equals n, will never cross itself because there are no repeated positions. Similarly, a path with repeated movements that do not lead back to a previously visited position, for example, path equals NNNN, will also return false. However, if the path returns to the starting position, such as in path equals NESWW, the output will be true because a crossing occurs. Additionally, because the path length can go up to 10,000, the solution must be efficient to handle these long inputs without performance issues. Efficient handling of such cases is critical for solving this problem within the constraints. To solve the problem, we need to determine if a path described by a string crosses itself. The string consists of movement directions n, s, e, and w representing movements on a Cartesian grid. The key idea is that a path crosses if the same grid point is visited more than once. Each movement directly changes the coordinates: n increases the y-coordinate by 1, s decreases the y-coordinate by 1, e increases the x-coordinate by 1, and w decreases it. By keeping track of visited positions, we can efficiently check for crossings. To start, we initialize the set of visited positions with the starting point, 0, 0, since the path begins there. This allows us to account for any immediate return to the origin as a valid crossing scenario. There are multiple ways to approach this problem. The brute force method involves maintaining a list of all visited positions. For each new position, we calculate its coordinates and check if it already exists in the list. If it does, we conclude the path crosses; otherwise, we add the position to the list and continue. However, this approach is inefficient, with a time complexity of n squared, because each membership check requires scanning the entire list. A more efficient solution uses a set instead of a list. Sets allow us to check membership in 1 time on average, making this approach much faster. Here, we start by adding the initial position, 0, 0, to the set. As we iterate through the path, we update the current position based on the movement direction. If the new position is already in the set, the path crosses, and we return true. Otherwise, we add the position to the set and proceed. If no crossing is detected by the end, we return false. This optimized approach reduces the time complexity to O(n), as each position is added to the set only once. The set-based solution is both efficient and straightforward, but alternative methods exist. For instance, a hash map can be used to track positions and their visit counts. In this approach, positions are stored as keys in a dictionary, with their values representing how many times each position is visited. For every new position, we increment its count. If a position's count exceeds 1, we know the path crosses. While this method also has a time complexity of O(n), it is less memory efficient than the set-based approach because it stores unnecessary visit counts. The simplicity and minimal memory usage of the set-based approach make it the preferred choice for this problem. By focusing solely on detecting repeated positions, the set approach avoids the overhead of storing additional data, while still achieving linear time complexity. This balance of efficiency and clarity is a key advantage. While the set-based solution is highly efficient, it is worth noting a minor trade-off. The average case time complexity of set operations is O(1), but in rare cases, hash collisions could degrade performance to O(n). However, for reasonable input sizes, this is unlikely to be an issue in practice. The brute force approach, while conceptually simple, is computationally expensive with its quadratic time complexity, making it unsuitable for long paths. The hash map approach, on the other hand, is comparable in time complexity to the set approach but introduces unnecessary memory overhead. With these trade-offs in mind, the chosen strategy, using a set, offers the best balance of simplicity, efficiency, and practicality. In conclusion, the final solution achieves a time complexity of O(n) and a space complexity of O(n), making it an optimal choice for detecting path crossings in this problem. In this problem, we are working with a path described by a sequence of movement directions represented as a string containing the characters N, S, E, and W, which stand for north, south, east, and west respectively. Each character in the string corresponds to a single step on a Cartesian grid. Our goal is to determine whether the path crosses itself, which happens when a grid point is visited more than once during the traversal. To solve this, we begin by initializing two key elements, the current position, which starts at the origin, 0, 0, and a set called visited to keep track of all positions encountered along the path. The origin, 0, 0, is added to this set as the starting point. Next, we define how each movement direction affects the coordinates. For example, moving north increases the y-coordinate by 1, while moving south decreases it. Similarly, moving east increases the x-coordinate, and moving west decreases it. With these rules in place, we are ready to process the string character by character to simulate the path traversal. As we process each character in the string, we update the current position based on the movement rules we just defined. For instance, if the direction is n, we move one step up by increasing the y-coordinate. After updating the position, we need to determine whether this new position has been visited before. This is where the visited set comes into play. If the current position already exists in the set, it means the path has crossed itself, and we can immediately return true. If the position is not in the set, we add it to the set and continue processing the next direction. Once all characters in the string have been processed, if no crossings are detected, we return false, indicating that the path does not cross itself. Key insights here include the use of a Cartesian grid to represent each position as a unique x, y pair, and the efficiency of the set data structure, which allows us to check for previously visited positions in constant time on average. This algorithm is particularly efficient because it terminates early if a crossing is detected, and it handles various edge cases, such as paths that never cross, paths that return to the starting point, or even very long paths without crossings. The algorithm relies on two main data structures, a set and a variable to track the current position. The visited set stores all the grid positions encountered during the traversal, and it is chosen specifically for its average O(1) time complexity for both insertions and lookups. The current position, represented as an x, y coordinate, is updated dynamically as we process each movement direction. In terms of complexity, the time complexity of this solution is O(n), where n is the length of the input string path, because we process each position exactly once and perform constant time operations for updates and checks. The space complexity is O(k), where k is the number of unique positions visited. In the worst-case scenario, this would equal the length of the path if all positions are distinct. To illustrate the algorithm, consider the path NESWW. We start at 0, 0, and add it to the visited set. Moving north takes us to 0, 1, which is added to the set. Moving east takes us to 1, 1, and then moving south brings us to 1, 0, both of which are also added to the set. Finally, when we move west, we reach 0, 0 again, which is already in the visited set. This indicates a crossing, so the function returns true. On the other hand, for a path like NNNN, we start at 0, 0, and move up 4 times, reaching new positions each time. Since no position is revisited, the function returns false. The algorithm is implemented in Python by maintaining a set for visited positions and updating the current position as we iterate through the string. For each movement direction, we adjust the x or y coordinate accordingly. If the new position is already in the visited set, we return true. Otherwise, we add the position to the set and proceed. If the loop completes without encountering a crossing, we return false. This implementation efficiently handles both typical and edge cases, ensuring correctness and optimal performance. This implementation solves the problem of determining whether a given path crosses itself on a Cartesian grid. The solution uses a set to track visited points, ensuring efficient lookups. First, we initialize the starting position at the origin, 0, 0, and create a set to store visited positions. The origin is added to the set as the initial point. Then, we iterate through each character in the path string. Each character represents a movement direction, N for north, S for south, E for east, and W for west. Depending on the direction, we update the coordinates, x, y, accordingly. After updating the position, we check if the new coordinates already exist in the visited set. If they do, it means the path has crossed itself, and we immediately return true. Otherwise, we add the current position to the set and continue the iteration. If the loop completes without finding any revisited position, we return false, indicating that the path does not cross itself. This approach is efficient, with a time complexity of O, n, where n is the length of the path. The set operations, add and lookup, are O, 1, on average, making the solution well suited for the problem constraints. Here, we start our Java implementation by importing the necessary packages and defining the solution class. Inside the class, we have the method isPathCrossing, which takes a string path as input. The first step is to initialize the starting coordinates, x and y, both set to 0. These represent our initial position on a grid. To track all visited positions, we use a hash set of strings, as it provides an efficient way to check whether a position has been visited before. The starting position, represented as the string 0, 0, is added to the set to mark it as visited. Next, we iterate through each character in the path string. For each direction, we update the x or y coordinate accordingly. For example, moving n increments y by 1, while moving s decrements it. Similarly, e increments x, and w decrements x. Each new position is then converted into a string key using the format x, y, which will help us track it within the hash set. Once we have the string key for the current position, we check if this position already exists in the hash set. If it does, this means the path has crossed itself, and we immediately return true. If not, we add the current position to the set to mark it as visited. This ensures we can continue tracking all previously visited positions as the path progresses. After processing all the characters in the path, if no crossing is detected, the method returns false, indicating that the path does not overlap. This implementation efficiently determines whether a path crosses itself by leveraging the hash set's ability to quickly check for duplicate entries, ensuring optimal performance even for longer paths. To solve this problem, we start by initializing our starting position at the origin, which is 0, 0. We also create a set called visited to keep track of all the positions we have visited so far, and initially, it contains just the origin. As we process the first step in the path, which is n for north, we move up by incrementing the y coordinate by 1, resulting in the new position, 0, 1. Since this position is not already in the visited set, we add it. Then, we move to the next step, E for east. Here, we increment the x coordinate by 1, moving right to the position, 1, 1. Again, this position is not in the set, so we add it. At this point, the visited set contains 3 positions, the origin, 0, 1, and 1, 1. Now, we process the next step, which is S4 south. Moving down means decrementing the y-coordinate by 1, taking us to the position 1, 0. This position is not in the visited set, so we add it. At this stage, the set includes 4 positions, the origin, 0, 1, 1, 1, and 1, 0. Since we have reached the end of the path and no position was revisited during the traversal, we return false, indicating that the path does not cross itself. This concludes the first example. In the second example, the path is NESWN. Again, we start at the origin and initialize the visited set with 0, 0. Processing the first step, N, we move up, resulting in the position 0, 1, which is added to the set. The next step, E, moves us right to 1, 1, and since this position is new, we add it to visited. Then, S takes us down to 1, 0, which is also added to the set. At this point, the visited set contains 4 positions, 0, 0, 0, 1, 1, 1, and 1, 0. Next, we process W4 west, which moves us left to the position 0, 0. However, this position is already in the visited set, meaning we have revisited a position and the path crosses itself. As a result, we return true. For the third example, the path is NNNN. Once again, we initialize at the origin and add it to the visited set. The first step, N, moves us up to 0, 1, which is added to the set. The visited set now contains 2 positions, 0, 0, and 0, 1. We continue moving north with the next step, reaching 0, 2, and adding it to the set. Then, another step north takes us to 0, 3, which is added as well. Finally, one more step up brings us to 0, 4, and this position is also added to the visited set. At the end of the path, the visited set contains 5 distinct positions, 0, 0, 0, 1, 0, 2, 0, 3, and 0, 4. Since no position was revisited during the traversal, we return false, indicating that the path does not cross itself. This concludes the third example. The time complexity of the solution is O, n, where n represents the length of the input string path. Let's break this down step by step. First, during initialization, we set up variables x and y as integers and create the set visited, adding the initial position 0, 0. These operations are constant time, so O, 1. The main contribution to the time complexity comes from iterating through the input path. The for loop processes each character in the string, which runs n times. Within each iteration, updating the coordinates x and y based on the direction, checking if the current position exists in the set, and adding a new position to the set. All of these operations are O, 1 on average. Since the loop runs n times and each iteration consists of constant time operations, the overall time complexity sums up to O, n. Finally, the return statement at the end of the function, which simply returns a Boolean value, is also O, 1. When we combine all these operations together, initialization, iteration, and the return, the total time complexity of the solution is O, n. Now let's examine the space complexity. The primary factor here is the set visited, which stores all unique positions visited during the traversal. In the worst case, all positions are unique, so the size of the set is proportional to the number of steps, k, where k is less than or equal to n. Storing each position as a tuple of 2 integers takes constant space, so the total space used by the set is O, k. The integer variables x and y also use constant space, so their contribution to overall space usage is O, 1. Additionally, the input string path itself takes O, n, space. However, since this is part of the input and not additional memory allocated by the algorithm, it's not included in the extra space calculation. Therefore, the overall space complexity is O, k, where k is the number of unique positions visited, and k is always less than or equal to n. Now let's consider different cases. In the best case, where the path does not cross at all, the algorithm still iterates through the entire path, resulting in O, n, time an O, n, space for storing the unique positions. In the worst case, if the path crosses early, the algorithm terminates after processing only a few steps, leading to minimal space usage, O, 1, while still taking O, n, time up to the point of crossing. On average, the algorithm processes all n steps and uses O, k, space, where k depends on the number of unique positions encountered. When comparing this optimized approach to a naive one, the difference in efficiency becomes clear. A brute force solution might involve storing all positions in a list and checking for duplicates using nested loops. This would result in a time complexity of O(n) squared, because of the repeated comparisons, while space complexity would remain O(n) due to storing the positions. In contrast, the current solution optimizes duplicate checks using a set, reducing the time complexity to O(n), while maintaining space complexity at O(k). The use of a set ensures that membership checks and insertions are O(1) on average, making the algorithm highly efficient. Since all operations in the loop are constant time and the loop runs n times, the time complexity is mathematically proven to be O(n). The space complexity depends on the number of unique positions visited, which is O(k), where k is always less than or equal to n. There are a few common mistakes to watch out for when solving the path crossing problem. First, failing to handle revisits properly can cause you to miss when the path crosses itself. To avoid this, make sure to keep track of all visited points using a set or a similar hash-based structure, as these allow efficient checks for duplicates. Another frequent issue is updating coordinates incorrectly based on the direction. For example, moving north should adjust the y-coordinate, not the x-coordinate. Double-check your updates for each direction to prevent errors. Inefficient data structures can also trip you up. Using a list instead of a set to store visited points results in slower performance, as checking for duplicates in a list takes O(n) time, leading to an overall O(n) squared complexity. Always use a set for O(1) lookups. Additionally, edge cases like revisiting the starting point, handling empty strings, or working with single character paths are often overlooked. These scenarios can lead to incorrect results if not addressed explicitly. Finally, some may try to modify the input path string during processing. This is unnecessary and can introduce errors. Instead, focus on iterating through the string while dynamically calculating coordinates based on the directions provided. This problem is a great opportunity to showcase your ability to simulate movement on a grid and track state efficiently. It tests your understanding of hash sets, coordinate systems, and handling edge cases. One key optimization to discuss is the use of different data structures. For instance, comparing a set to a list highlights how a set's O(1) lookup time is far more efficient than a list's O(n) searches, especially as the input grows. This is why O(n) solutions are preferred here. Additionally, recognizing that this problem is part of a broader category of grid traversal problems can help you identify patterns. These strategies are transferable to similar questions, making it easier to approach related challenges. Speaking of related problems, you might encounter questions like LeetCode 980, which involves unique paths, or LeetCode 141, which focuses on detecting cycles in a linked list. Both involve similar concepts of tracking state and detecting revisits. Problems like LeetCode 1036, which deals with escaping a maze, also align with the grid traversal theme and can build on your understanding of this problem. There are several approaches you can use to solve this problem, each with its own trade-offs. The most optimal approach involves using a hash set to track visited coordinates. This ensures O(1) lookups and gives the solution an overall time complexity of O(n). The trade-off here is that it requires additional space to store the set, but this is a worthwhile compromise for the performance gain. A less efficient approach would be brute force, using a list to store visited points and checking for duplicates with each step. While simpler to implement, this method has an O(n) squared complexity due to repeated searches, making it impractical for large inputs. Another alternative is to explicitly represent the grid as a 2D array, marking cells as visited during traversal. While this can work well for small grids, it becomes memory intensive as the grid size grows, making it less suitable for scenarios with large or unbounded grids. Each of these approaches has its strengths and weaknesses, so understanding the trade-offs is key when deciding which to use. Great job following along. To summarize, we used a hash set to track visited coordinates and efficiently detected if the path crossed itself. This is a valuable technique for grid-based problems. Thanks for watching, and don't forget to subscribe for more problem-solving content. See you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!